So yeah, this is my talk, task execution with behavior trees. My name is Chris, and my supervisor is Peter Algren, and my project is about robust mission planning and execution. So before I go into details, I want to give a bit of a background for our YouTube listeners, or watchers rather. SMaRC has three application areas. There's environmental monitoring, safeguarding society, and ocean production. And in all these scenarios, we have to use an AUV like this one to accomplish different tasks. So environmental monitoring, it could be like going near a glacier. Safeguarding society could be monitoring some area for security. And then ocean production could be some sort of agricultural project. So the thing that all these places have in common is that they require gathering data in environments that are accessible, unstructured, dynamic, and varying over time, which makes it really complicated. So we need systems that are robust and can accomplish these things. And one of the best examples of these characteristics is in polar regions. I mean, there it's just crazy. Your AUV is just gone for hours, and the environment is unknown, and everything's moving around. Yeah, so all these environmental characteristics require fault tolerance, clever localization, among other things. And yeah, all these things have to be achieved in a system that's autonomous, efficient, and safe. So what's conventionally done is people use a finite state machine, which works, but they're limited to operator expectations, and they can be a bit inflexible. So recently, interest has shifted towards goal-based systems, where instead of reacting to a state, you're executing some action based on a desired goal. And so one of such systems is behavior trees. They generalize a number of different planning architectures, but most importantly, they're robust, and they help to achieve priority of safety in a modular way, which means that they're easy to program, and there's less possibility for human error. And on the right here, you can see an example of a behavior tree. So this is an example of a goal-orientated structure here. So your goal is to go inside a house, but in order to go inside the house, the door has to be open. And so, yeah, you're planning with a goal in mind, basically. And so in my project, we first started looking at behavior trees for AUVs in collaboration with the National Oceanographic Center in the UK. And they wanted to start using BTs. And so we did a project with them, and we looked at their typical mission plan, which has all these steps outlined here. Most of the time you have some prescribed waypoints that you want to navigate through, but you also want to be able to autonomously add new waypoints based on different things, like Luis mentioned, points of interest. Like if you detect an interesting object, add some new waypoints and do that autonomously without any user input. But you also want to make sure that the architecture is safe. So like if you get a leak in your vehicle, you autonomously abort, for instance. And so behavior trees are really well suited for this type of mission execution. So if you don't know what a behavior tree or how a behavior tree functions, it's kind of like this. You have different branches of the tree that are dedicated to different purposes. So as I mentioned, there's safety. That's the first priority up there on top. And then down below, you have stuff like mission execution, which is just like going through waypoints. So the behavior tree kind of works like this. A tick comes in, and it checks the first thing, is the vehicle safe? If it is, then it returns success. And then, yeah, based on these composition nodes, which I'll describe a bit later, the tick then gets moved to the next branch. So have we received the continue command? Nope. So then we need to prepare the system. Returns running. and then it just continues. So for example, here we tick mission complete. It's not, so that returns failure. So then that means we need to execute the mission. So then we execute the mission, and that runs for a while, and then eventually eventually the mission is complete, and then we need to finalize it, and eventually it's finalized, and then it's complete. So we can take the general structure that I just showed, and we can expand it for different things. And this is actually what we did on SAM, our AUV. And our first test was in Vastervik about, I think it was like 2 years ago. But yeah, so we took that structure and we put it on SAM, and we're still using that same structure, just expanding it as we go into different scenarios. And so in fact, we used it for a cool scenario last year, which is where we did a target search for a car. It was a submerged Mini Cooper. And it was that point of interest behavior that we mentioned, where you detect something and then you plan some waypoints around that. So then this year, we're going to look at a new scenario, which is going through an algae farm. And so all this stuff is using behavior trees because of the characteristics we described before. Yeah, so the main advantage of behavior trees is that they're really modular. So different behaviors can be added really easily. The thing is, most behaviors in a behavior tree are described by some sort of continuous time dynamics, where you have like some sort of continuous controller, like if you want to follow a trajectory or something like that. But despite that, most behavior tree formulations are in discrete time. So this is kind of interesting. So this is the research I've been pursuing. So we decided to start researching or formulating rather behavior trees in continuous time. So a behavior tree is pretty much just a function, like you have up here on top. It's a function composed of f, which is a differential equation, r, which is a return status, which can be equal to running, success, or failure, and then a time step, which is basically the frequency of those ticks that I showed before. But in order to formulate this in continuous time, we actually took away this time step, and now it's just a differential equation and a return status. And now there is no time step, it's just continuous time. Yeah. So what we're going to do for the rest of this presentation is we're going to show how behavior trees are actually, or they can be interpreted as discontinuous dynamical systems. So before we continue, first, if you take that return function that we showed before, which could be equal to running, success, or failure, and then you look through the state space at where those return statuses are well defined, you get these regions. So big R is this running region, success is this region here, and F is this region here. And these are separate from each other, and they cover the whole they cover the whole state space. So that means they're pairwise disjoint. And so yeah, we're going to use these regions to define more complex behaviors. And to do that, we first need to look at these things called compositional behavior trees. And there's a couple of different of these types of behavior trees, but the two primary ones are fallbacks and sequences. So in a fallback, if one of these children fails, like a tick comes in, this guy fails, then it's going to go to the next one, and then so on. So then this overall behavior tree here will only fail if all of its children fail. But if any of its children succeed, then they're going to be able to return success. And then it's the opposite for this sequence composition over here. So using these two compositions, we can make a bunch of different complex behaviors. A behavior tree is, like as the name implies, it's a tree, which means that it's a directed acyclical graph. And this is an example of what it would look like. And these subscripts here are just arbitrary. They're just used for notation in the presentation. Yeah, but they're not just any tree. They're actually order trees, which means that the order of the children matters. So like, for instance, these children here, we need to know that D comes before E, and we need to know that G comes before H. So in order to describe this architecture, we actually used order theory, which is it's sort of related to graph theory. Sometimes it can look a bit complex, but actually order theory is everywhere. And I think most of you are familiar with the order of integers, for instance. So -5 comes before -4, and then so on. So actually, these types of orders can actually order really anything you want. So in order to describe order trees, we use these orders to order children and to order ancestors. So here's some examples here. So D comes before E, G comes before H, and then with respect to sibling order. And then there's also the ancestor order. So like A comes before C, C comes before D, and so on. And so we can use those orders to actually get more complex orders. So for instance, here we have the uncle order. So basically what that does, it allows you to compute what the sibling to the left of a node itself or one of its parents is. So yeah, for instance, here we have an uncle of E would be D or B, for instance. And so using that, we can compute this thing called the influence region, which is it basically uses the functionality of the composition nodes that we had before to basically get the region in which a behavior tree is running. So, or not running, but being executed. So if the state is within this influence region, so like for instance, H, if X is in influence region of this behavior tree H here, then that means that the state is in the success region of G, failure region of C, and B. And so using that, we're able to, we're able to basically say which behavior tree is running based on where we are in the state space. And so another thing of interest is which behavior trees can actually turn success or failure. And in a behavior tree, that would be like a node that can return success would not have a there wouldn't be any behavior trees to the right of it preventing it from returning success. And that's basically what these equations mean. You don't really have to understand them fully, but for instance, here in this tree, the nodes that are capable of returning success to the root are these guys. So B can return success, E can return success, and H can return success. And then for failure, it's G and H. They can return failure. So using these, we come up with these things called recursion regions. And these are actually the regions in which a leaf behavior tree would be executed. So so these sets actually have a special structure. It's like a laminar set family. And a laminar set family is basically just like a nested family of sets like this. And yeah, basically what these regions allow us to do is formulate a behavior tree as a dynamical system. So if we're just interested in the dynamical behavior of the root, which we usually are, then we can just take the differential equation of the root and then use those recursion regions to formulate a discontinuous dynamical system, or sometimes also referred to as a state-dependent switch system, or a hybrid system without jumps. So that's really cool, because what that allows us to do is use any of the variety of continuous time control methods for these systems. So for instance, like optimal control or Lyapunov stability analysis. So if we really want to test the robustness of our planning systems, this offers an avenue for us to use these tools, like Lyapunov stability, to actually assess the robustness. And further, this kind of formulation makes sense for AUVs in particular, because AUVs are actually non-holonomic systems. And it's pretty well known that non-holonomic systems aren't always stabilizable by continuous feedback. So an example of such a system is a unicycle car model. You can't always use continuous feedback to park it. And it's the same case with an AUV. There's some set points that require discontinuous control. And the formulation that we just gave allows us to formulate control policies like that. And so this formulation actually allows us to do some analysis into what behavior tree structures are good. And by good, we mean behavior trees that that guarantee that success will be achieved. Yeah, so we just want all high-level goals to be achieved. So if we consider each of the leaf behavior trees in a behavior tree, and we consider that all of them have some sort of attraction region, then we can actually assess basically the traversal map of all the different behaviors in a behavior tree. And so what that gives us is a traversability graph. And in our paper that we're about to submit, we actually use this in a general theorem. So if the traversability graph of all these different leaf behavior trees forms a directed acyclical graph, and all the endpoints or the sinks end up in some success region, then the overall behavior tree is successful. Of course, there's some limitation to that, and that's if there is a cycle. Although we have come up with some tools to make sure that behavior trees are still successful even if there are cycles. But yeah, this is basically what it looks like. And so the conclusion of this is that there's two things that one needs to consider when designing a behavior tree. It's both the behavior tree graph structure, like the actual structure of the tree itself, and the attraction regions of the controllers. And so the tools that we developed in our paper actually allow you to analyze the BT graph structure and the controller regions of attractions all together to assess whether the behavior tree will be successful. And so in our paper, we also applied this general theory to some common architectures like the post-condition and precondition action behavior tree, which as an example, we have this one on the right. And then there's also another architecture called implicit sequence BTs, which is the behavior tree I showed before. Yeah, and that's not the only research I've done. There's some other parallel work that I've been doing as well. in my PhD, I like to think that like there's two parts. The first part is looking at like the high level stuff, like the planning aspect, and then also we have to look into the specific behaviors themselves. So another thing I've been looking at is informative path planning, which is basically the problem of what is the optimal control to map an area, basically, to some level of certainty. So to do this, I recently looked into using reinforcement learning and Gaussian processes to basically learn like an optimal policy to map an area with the Gaussian process. And it actually works, but there's some limitations with the reinforcement learning part. Reinforcement learning is a bit susceptible to local minima, so in such a complex problem, it's difficult to get something that really works. But it still worked nevertheless. So basically, our policy learns what the optimal behavior is to map an area to some certainty, and it actually outperformed a lawnmower path. So this number up here is just like the uncertainty of the map. So the reinforcement learning policy outperformed the lawnmower. Yeah, and then I've also been looking into using stochastic variational Gaussian processes to include localization uncertainty. And that's ongoing work with Ignacio. Basically, we want to do informative path planning, but also taking into account the localization uncertainty. But the problem with bathymetry from AUVs is that there's so many points, and most conventional Gaussian processes don't really allow you to use that many points. And that's why we're looking at stochastic variational Gaussian processes, because they allow you to take in millions of points. And then also, Sriharsha and I are supervising a master's student, Bobby, and he's looking at learning the dynamics of our AUV with these things called Lagrangian neural networks, which is a subset of physics-informed learning. And yeah, the results are pending, but we're hopeful that we'll get something good. That's all I have.